Another basic organic chemistry class. Today's class will be looking at alcohols. Alcohols are aliphatic hydrocarbons that contains hydroxy group in sp3 hybridized form. So when hydroxy group loses a hydrogen, it becomes alkyl. When this hydrogen lost is replaced with hydroxy group, it becomes alkanol. From alkyl we have ol, that is alkanol. These alcohols are classified into three: primary, secondary, and tertiary. The simplest way to differentiate between these classes of alcohol is that primary alcohol, the carbon that bears the hydroxy group, has two hydrogen. Secondary alcohol, the carbon that bears the hydroxy group, has just one hydrogen. While tertiary alcohol, the carbon that bears the hydroxy group does not have any hydrogen. They are all filled with alkyl groups. Hydroxy group can also be seen in a compound that is unsaturated, which is called enol. So we can have, instead of have alkanol, we can have alkanol. And this can also be seen in aromatic ring in form of phenol. Just like benzene is sp2 hybridized, phenols are also sp hybridized. So the carbon in phenol and the carbon in benzene have the same hybridization, which is sp2 hybridized because of double bond. Every double bond is sp2 hybridized. In terms of hybridization, oxygen atom in alcohol, ether and epoxide, all are sp3 hybridized. The bond angle around the atom of oxygen in alcohol is similar to that of normal sp3 hybridized, which is 109. But in terms of ether, the bond angle is higher, which is 111, because ether has alkyl as a terminal atom, while alcohol have hydrogen. So the bond in ether is more extended than that of alcohol. When we talk about nomenclature, we talk about naming. In aliphatic hydrocarbons, when you want to name, you don't consider anything. What you consider is to follow the routes that will give the substituent the minimal number on the ring. But in the case of alcohol, we are going to give priority to alcohol because alcohol is a functional group. So we're going to follow the route that is going to give this hydroxy group the minimal number. If you're coming from my right, the position of hydroxy group is 3. If you're coming from my left, the position of hydroxy group is 4. So we're going to follow my right, making it 3 all. Then any other thing becomes a substituent. So that's why we have 5-methyl 3-hexanol. We can also call it 5-methyl hexan 3-ol. Any of these routes, any of this naming method is acceptable, but it's very advisable you know the two in case you're dealing with CBT and they are not using 5-methyl hexan 3-ol. They're using 5-methyl 3-hexanol. So you understand that they are the same. When naming and you want to name a ring, the functional group still takes priority, but you're going to follow the routes when there are substituents to give the substituent minimal number. In the first ring, we are having 3-methyl cyclohexanol because we are following the routes that will give this methyl the minimal number. So we're going anti-clockwise, giving priority to hydroxy group being the functional group. The same thing happened in the second compound. We are giving hydroxy group the priority. So we're following the routes that will give this substituent, the other substituent, the minimal number. When secondary alcohol can also be called isopropyl alcohol as a common name. So in terms of substituents, if you have options in CBT, and you have this. The other name for secondary alcohol, the name of this compound in IOPAC is propan-2-ol or 2-propanol. So another name for that, the common name is isopropyl alcohol, which is a secondary alcohol. Looking at it, the carbon that bears the hydroxy group is having just one hydrogen. That's what makes it secondary alcohol. In the spirit of nomenclature, when there are more than one hydroxy group, when there are two, we call them diol, that is 2 ols. When there are 3, we call them 3 ols. When there are 4, we call them tetraols. So di, tri, and tetra indicate the number of hydroxy group in the compound. The physical properties of alcohol. Alcohol have dipole-dipole interaction because they have a bent structure with 2 polar bonds. And there is existence of intermolecular hydrogen bonding because there is hydrogen bonding between the oxygen and hydrogen in the same ring. So alcohol have intermolecular hydrogen bonding, which also talks about why it has high boiling point than alkane of the same molecular weight. In steric effect affects the hydrogen bonding, meaning that tertiary has less hydrogen bonding while primary has more hydrogen bonding. So the more the steric hindrance, the lesser the hydrogen bonding. So steric because when there are methyl, there are no availability of hydrogen to bond. So the more the hydrogen, the higher the hydrogen bonding. So steric effect hinders hydrogen bonding. In terms of physical properties, because of the existence of hydrogen bonding, alcohol has a higher boiling point than ether and alkane of corresponding molecular weight. And increase in boiling point increases with hydrogen bonding. Like we said in the previous slide, that's why primary has higher boiling point than tertiary because of hydrogen bonding. In terms of solubility, alcohols are soluble more than ether and alkane of comparable molecular weight. In treating alcohols, we can obtain this alcohol from simple fermentation of grapes. That is where red wine comes from. So whenever you're taking red wine, you'll be happy that this is as a result of natural reaction, which is called fermentation of grapes. That's where red wines are potent source of antioxidants that are very healthy for the heart. Methanol is also an alcohol that has been used but is very toxic. There was a time where people consumed alcohol, that's ethanol, that is contaminated with methanol, which caused many souls to die. So it's very, very dangerous to the kidney, but it's very useful in the lab for extraction. Propan-2-ol or 2-propanol is also what is known as rubbing alcohol. It's very useful, especially in treating or sanitizing wounds or surgical instruments. Ethylene glycol is an alcohol that is known as a major component of antifreeze, but they are also very toxic. So these are interesting alcohol around you. So when you see them, you appreciate them. Appreciate that chemistry is life. How can this alcohol be prepared? We have two major methods. We can prepare them industrially or in the laboratory. In industry, petroleum raw materials have been proven to be a source of most of alcohol, especially ethanol and methanol. And there is another method, which is ancient method, fermentation of starchy products and distillation of wood and coal are also potent sources of alcohol in the industry. Details. When 2 volumes of hydrogen and 1 volume of carbon monoxide, which is synthesis gas, are mixed we are going to form alcohol. This is what happens in the lab, and the alcohol produced this way is called methanol. This is a major process they use in production of methanol in the industry. In industry, alkane can also be hydrated to form ethanol by using sulfuric acid as a catalyst at a very high temperature. This is method of obtaining ethanol from the industry. Another method of obtaining this alcohol, especially ethanol, is fermentation of carbohydrates. When carbohydrates are, first of all, sucrose is going to be converted to glucose and fructose using an enzyme called invertase. Then this glucose and fructose are going to be converted to alcohol using a yeast, an enzyme called zymase, which is available in yeast. So this is another ancient method of obtaining alcohol. Most interest is in the lab. Alcohol can be obtained in lab using the following methods. In these methods, functional groups are being 7 different functional groups are being converted to alcohol. We have ethers, we have ketones, or that's carbonyl compounds, ketone and aldehyde. We have alkane, we have alkyl halide, carboxylic acid, acid chloride, esters, and epoxide. So we're going to look at them one after the other. Preparation of alcohol from the lab using alkane is a simple method of hydration, which is similar to what is done in the industry. Hydration is simple addition of water. So when water is being added, this method follows Markovnikov's rule, in the sense that when an alcohol is asymmetric, the carbon that have the more hydrogen is going to collect the hydrogen. The carbon that have the less hydrogen will collect the hydroxy group, following Markovnikov's rule. This is also for asymmetrical compound. But looking at what we have, the compound is asymmetrical. The compound is symmetrical. When a compound is symmetrical, it means that I can divide them into 2 equal halves. When a compound is symmetrical, Markovnikov's rule is not necessary. We talk about Markovnikov's for asymmetrical compounds. Hydrolysis of alkyl halide. When you're talking about hydrolysis of alkyl halide, hydrolysis means addition of hydroxy group into a molecule. So in this case, either we are using potassium hydroxide or silver oxide in boiling water. The essence is we are looking for a source of hydroxy group. So there is exchange of hydroxy group with halide to form our alcohol. Reduction of all the carbonyl compounds, esters, and acid. This is achieved using reagents. Hydrogenation is a reductive reaction. So anything that can hydrogenate alkane to alkane can also reduce aldehyde and ketone and acid to alcohol. Now, traditional reducing agents are sodium in ethanol, sodium in mercury with solvent of ethanol or solvent of ether or alcohol. But commonly, we use hydrogen molecule in either platinum, palladium, or nickel as a catalyst. So any of these can do the reduction. But there are complex hydride, which are group 1 and group 3 metals. Example is lithium aluminum hydride and sodium borohydride. These solvents can also be used in. But when you are reducing a compound that has unsaturation and you want to preserve this unsaturation, that's double bond, you don't use hydrogen in platinum, nickel, or palladium. You go ahead and use this lithium aluminum hydride or sodium borohydride, because they are going to convert the carbonyl compound to alcohol without affecting the double bond. But because sodium borohydride is milder, it cannot work on acid and ester, but it can work on aldehyde and ketone. So when I want to reduce acid and ester, I don't use sodium borohydride. I would rather use lithium aluminum hydride to achieve that. So that is as seen in the equations. Looking at the reaction for aldehyde to from aldehyde to alcohol, molecule of hydrogen and platinum is used. So you can also use sodium and ethanol, or any reducing agent can be used. Even the complex hydride can also be used. But when you're dealing with acid, you don't use even sodium borohydride. You use lithium aluminum tetrahydride. So use that for acid and esters. So from the slide, you realize that whenever you are reducing aldehyde, you're getting primary alcohol. When you're reducing ketone, you're getting secondary alcohol. Then when you want to protect the unsaturation, you use either sodium borohydride or lithium aluminum tetrahydride. But when you want to saturate the unsaturation and also reduce the aldehyde to alcohol, you use hydrogen in platinum, in nickel, or in palladium. So you're doing both hydrogenation, and which is a reductive reaction, and also converting the aldehyde to alcohol, or carbonate to alcohol. When reducing esters, you're going to obtain two alcohols. Why? Because esters are formed by acid and alcohol. When acid reacts with alcohol, form an ester. So when I want to reduce, I'm going to form two alcohols. One is that the acid aspect of the ring is going to form primary alcohol, because reduction of acid is going to form an alcohol. Then the other one is going to also form the alcohol that is being used. So the most important thing, whenever I'm reducing ester, the acid aspect must be primary alcohol. So the other terminal alcohol would be dependent on the alkyl that form the ester. Remember, when I'm reducing ester, I don't use any other thing except lithium aluminum tetrahydride in presence of an acid. So it has to be acidified lithium aluminum tetrahydride. Now, another method of preparing alcohol is using Grignard reagent. This Grignard reagent, which is represented as RMDS, can be used. Alcohol can be formed using aldehyde, ketone, esters, or epoxide to form primary, secondary, or tertiary. Then after them, it's followed by hydrolysis to form an alcohol. So the Grignard reagent is going to form organometallic compound, which under hydrolysis forms alcohol, as we're going to discuss on upcoming slides. For primary alcohols, you can only use methanol, not all alkanal. Methanol is a compound that has just one hydrogen. So methanol forms primary alcohol. So in my methanol, according to the equation, you can understand that Grignard reagent is going to attack. Remember, for attack to come, the bond connecting carbon and hydrogen need to break to create a carbocationic species. That is where the bonding is going to take place. But all methanols are going to give you primary alcohol according to the equation. This is a mechanism, but just understand it. When you go through it, when you look at the mechanism, it's self-explanatory. Then the first stage is where we form our organometallic. Then under hydrolysis, we are going to form an alcohol. Simply put, the MgBr is being replaced with hydrogen, and others are, then the remaining hydroxy group is going to bond with MgBr to form a byproduct. So that's how alcohol is formed using Grignard reagent and methanol. Another name for methanol is formaldehyde. In case the way it comes in your CBT, whether they call it formaldehyde or methanol, we are talking about Grignard reagent forming primary alcohol. Then other alkanal except methanol reacting with Grignard reagent is going to form secondary alcohol using the same method. The most important thing is at the end, remember in methanol we are having two hydrogen, but now we have one hydrogen and methyl. So that methyl is going to help to form secondary alcohol. Remember, in primary alcohol, the carbon, the hydroxy group have 2 hydrogen. So that's what methanol gave us. But in other alkanal, we are going to have 1 hydrogen alone, making it possible for us to form secondary alcohol. So ethanol, propanol, or any other alkanal is going to form secondary, while methanol is going to form primary alcohol. So when we are talking about tertiary alcohol, we are not using methanol again, we are using ketone. Why? Because ketone has 2 alkyl group, no hydrogen. And remember, tertiary alcohol does not have any hydrogen. That's why ketone is the best compound to form a tertiary alcohol. In that case, we are still following the same mechanism, but instead of 1 hydrogen, we don't have any hydrogen. That's why we are going to form tertiary alcohol, because there's no hydrogen in tertiary alcohol. Now, when we are using ester, we are going to form tertiary alcohol. In this case, we are going to use 2 molecules of Grignard reagent. The first molecule is going to form a ketone, while the second molecule is going to form our ester. So remember, first molecule is going to form a ketone, then you just follow the method of ketone and Grignard reagent to form tertiary alcohol to complete the reaction of tertiary alcohol. So ester gives tertiary alcohol, Grignard reagent with Grignard reagent, ketone gives tertiary alcohol with Grignard reagent. Now, like methanol, oxide gives primary alcohol with Grignard reagent. In that case, the Grignard reagent you're going to have additional 2 carbon to form the primary alcohol, because oxide is going to give you 2 carbon. So if you're looking for primary alcohol and you're giving a Grignard reagent already, then the number of carbon would determine whether you want to use methanol or you want to use oxide. So when the question goes and you're forming a primary alcohol, look at the number of carbon and understand whether you're going to use oxide or you're going to use methanol. Remember, methanol is going to give you just 1 carbon. So looking at Grignard reagent and the number of carbon that ends in alcohol, if the number of carbon that ends in alcohol after the Grignard reagent is 2, you cannot use methanol, you're going to use oxide. So understand this. Another method of preparing alcohol is using hydroboration. Hydroboration is oxidative reaction where you talk about carbon-carbon double bond. This hydroboration involves 2 steps. The first step is hydroboration of the carbon. The other step is oxidation using peroxide in alkaline medium. These follow anti-Markovnikov's rule. Whenever you see in CBT exam, what you're going to come to your mind is that I'm going to form an alcohol using anti-Markovnikov's, meaning that the carbon that bears more hydrogen is going to have the hydroxy group. So that is a quick way of saying that whenever you see borohydride, hydrogen, and water and hydroxyl as a reagent, your compound is giving you an alcohol, but the alcohol is following anti-Markovnikov's rule. So that's a quick fix of understanding hydroboration reaction, especially as regarding your CBT. Chemical properties of alcohol. Alcohol are determined by the functional group OH. So it can react by either removing hydroxy group or removing just hydrogen. So both involve substitution of either hydroxy group or elimination of hydrogen in double bond. That's why alcohol are regarded as amphoteric. They can act as an acid and also as a base, just like. Now, as an acid, alcohol, remember, like Bronsted, is going to be a proton donor. Alcohol is going to donate proton, forming a conjugate base. Now, anything that stabilizes this conjugate base makes the acid to be very strong. So anything that stabilizes conjugate base increases acidity of the acid. So, but anything that destabilizes conjugate base is going to make the acid to be very weak. So the strength of acid depends on the factor that stabilizes the conjugate base. Now, from electron withdrawing substituents on this conjugate base is going to disperse the negative charge, thereby increasing acidity. So the electron withdrawing substituent is going to increase acidity, while electron donating is going to decrease acidity in a conjugate base. Very, very important. So whenever I have an acid, look at the substituent there. The substituent there, if it's electron donating, is going to decrease acidity. Electron withdrawing is going to increase acidity because of the negative charge that is going to be dispersed in by electron withdrawing, and when it's dispersed, it's going to increase acidity. But electron donating is going to destabilize the anion because there is high level of negativity. You're giving where there is excess. When you're taking where there is excess, it's stable. But when you're giving where there is excess, it's destabilized, making acidity to be reduced. So when acidity is reduced, basicity is increased. The chemical properties of alcohol. Alcohol can act as an acid when they react with active metal to give hydrogen and metal oxide, as shown in the reaction. When ethanol reacts with sodium metal, it's going to form sodium ethoxide. So in this case, it's reacting as an acid because it's releasing proton. There's exchange of proton and metal. So that's why we are calling it alcohol acting as an acid. As a base, alcohol is going to accept proton, like Bronsted said, forming a protonated alcohol. In this case, alcohol is acting as a base. The reactions of alcohol again is what we talk about Lucas reagent, Lucas test. In Lucas test, Lucas reagent, which is zinc chloride in concentrated HCl. Remember, it's not just HCl but concentrated. This is Lucas reagent. When we are doing Lucas test, we can use this method to validate the class of unknown alcohol. So when I put this Lucas reagent inside a compound that is unknown alcohol and there is no reaction at all, even if when heated it becomes slowly or never happened, I say that this alcohol is primary alcohol. But if this Lucas reagent is added and the reaction occurs within 1 or 5 minutes, we say this alcohol is secondary alcohol. But when this Lucas reagent reacts immediately into this alcohol, we say that this alcohol is a tertiary alcohol. So using Lucas reagent, we can classify alcohol that is not known. This is a reaction. Look at tertiary reacted immediately, secondary reacted after 5 minutes, primary under heat it will take, and now there's heat needs to come for primary to react, but in the lab at times it doesn't occur. So that's why we know distinguish primary, secondary, and tertiary. Ion is being replaced with hydroxyl radical. Another reaction of alcohol is it reacts with inorganic halide. This inorganic halide, there's always exchange of hydroxyl group with chlorine anion. What happens is that this inorganic acid can be phosphorus pentachloride, phosphorus trichloride, phosphorus pentabromide, or phosphorus tribromide. So if it's bromide, there will be exchange of hydroxyl group with that bromine. But if it's chloride, there will be exchange of hydroxyl and chloride. But when we are using sulfur dichloride oxide, which is called thionyl chloride, this reagent is better than others because the byproduct is gas, which will be eliminated. So we can get a pure acid alkyl halide without any contaminant, without any further work of purification. So that's why thionyl chloride is better than phosphorus penta or trichloride or bromide. So reaction with inorganic acid, there's exchange of hydroxyl and halide to form alkyl halide. So when alcohol reacts with inorganic acid, we are going to form alkyl halide. In esterification, which is when alcohol reacts with acid to form an ester, where we need a catalyst which can either be conc sulfuric acid or dry HCl. The excess there is going to help to remove the water in the reaction and put equilibrium to the right, which means helping the formation of the product. In esterification reaction, it is worthy of note that hydrogen is being donated by alcohol while hydroxy group is being released by acid, forming water. So in the byproduct of water, hydroxy group comes from acid while hydrogen comes from alcohol. That is why when they are forming the reversible reaction, the hydrogen is going to be given to the alcohol, while hydroxy group is going to be given to an acid. That's why the acid pattern is going to form primary alcohol. In terms of esterification, reactivity increases from methanol to primary, secondary, and tertiary. So that is the increase in esterification. So the more, the better. Oxidation. Alcohol can be oxidized to form acid depending on the class of alcohol. Primary alcohol is going to be oxidized to acid. Secondary alcohol is going to be oxidized to ketone. Tertiary is stable to oxidation. And the oxidizing agent commonly used is acidified permanganate, Jones reagent, which is sodium heptaoxodichromate in acid, or chromic acid. But when primary alcohol want to be limited, the essence is that, oh, I don't want to form an acid, my target is aldehyde. I don't go to this common oxidant. I'm going to use a unique oxidizing agent which is called pyridinium chlorochromate, known as PCC. This PCC is going to limit oxidation of primary alcohol to aldehyde. But if no other common oxidants are used, it's going to form acid instantly. So when the target is aldehyde, PCC is being employed. Secondary alcohol is always oxidized to ketone, but further oxidation is going to cause degradation. The bond is going to cleave and form acids. But tertiary is stable to oxidation. Tertiary alcohol are generally resistant to oxidation, especially under neutral or alkaline conditions. But in acidic conditions, this tertiary alcohol is going to cleave. There's going to be oxidative degradation to give acid and ketone as byproduct. But in a normal condition, they are stable to oxidation. They resist oxidation. Another reactions of alcohol is dehydration. Dehydration means removal of water. This dehydration occurs to form alkene. Remember, hydration moves alkene to alcohol. So dehydration is a reversible reaction of hydration. So in that case, the water that was added in hydration wants to be removed. So in this dehydration, we need an acid to do the work. Sulfuric acid can be used, or phosphorus oxychloride in the presence of a amine base. But normally the common ones are conc sulfuric acid. In this dehydration, which is an elimination reaction, the alpha carbon, which bear the hydroxy group, is going to remove the hydroxy group. Then the beta carbon is going to release the hydrogen. So that's why the two carbons, we call it alpha beta. The oxygen, the hydroxy group is removed from the alpha, while the hydrogen is being removed from beta carbon to form double bond, sp2. So we are moving from sp3 hybridized to sp2 hybridized. This is equation of dehydration. In terms of dehydration, primary are not easier, so the more the substituent, the easier dehydration. So tertiary are easily dehydrated and primary are poorly dehydrated. In mechanism, realize that tertiary are easily dehydrated and secondary because they go by E1 mechanism. In E1 mechanism, carbocation are being formed before elimination, while in E2 mechanism, both elimination and carbocation, everything happen in a single step. But this one is in double step, so because of that it is more stable. The first thing we are going to do when we are dealing with elimination to form alcohol using secondary and tertiary is to form a carbocation. That carbocation, before a base, is going to come and take the acidic hydrogen to form unsaturated system. The step of forming carbocation is using a sulfuric acid, which is a reagent, to protonate hydroxy group. Hydroxy group is a poor leaving group. When protonated, it becomes a good leaving group. When this hydroxy group leaves, it's going to create a cationic site. This cationic site, then the base, remember, the acid now has turned to base because it has lost hydrogen. So it's going to come back again to be regenerated, because acids are being regenerated, catalysts are being regenerated at the end of the reaction. For it to be regenerated, its base is going to come and take acidic hydrogen to be regenerated, forming the alkene we are looking for. So that's the mechanism of dehydration using for alcohol, for secondary and tertiary using E1 mechanism. Remember, there is always carbocation as transition stage. But for secondary, because of presence of hydrogen, there is always rearrangement to form a stable carbocation using 1,2 shift. In 1,2 shift is that alkyl is moved to the carbon that bears the hydrogen, making it a more stable ion, as you can see on the slide. Difference, everything that was done on for tertiary is still repeated here, but there is 1,2 shift to make this secondary carbocation to move it to tertiary, making it more stable, because tertiary carbocations are more stable than secondary. Then before the elimination by the acid to form the unsaturated alkene, which is our target. The next reaction of alcohol is iodoform or haloform reaction. This reaction is very unique because it only occurs by ethanol or propanol, because its iodoform reaction occurs for carbonyl compound or alcohol that have methyl attached directly to functional group. So if a compound does not have methyl, not ethyl, not propane, just methyl attached to the hydroxy group, it cannot undergo iodoform or haloform reaction. The first stage in this reaction is, so when the hydroxy group undergoes oxidation, we are going to form a carbonyl compound. That carbonyl compound will form halogenation and cleavage. Remember, just like ethanol, if ethanol undergoes oxidation, it's going to form ethanal, and in that ethanal, alkyl is connected to carbonyl compound, and that is why ethanal can undergo haloform. This haloform reaction is also obtainable in carbonyl compound. Why is obtainable in alcohol is because under oxidation, alcohols form carbonyl. So in carbonyl compound, the step of oxidation will be eliminated. We'll do halogenation and cleavage. Why we are doing oxidation here is that because we want to move from alcohol to carbonyl for us to do the halogenation, the halogenation and cleavage. But remember, the byproduct of iodoform or haloform reaction is triiodomethane, which is a yellow precipitate, and that is the iodoform we are talking about. And for a compound to undergo iodoform or haloform, it must have methyl attached to carbonyl, not ethyl, but methyl. That's why ethanol and propan 2 or or 2-propanol can undergo iodoform or haloform reaction. This class is well understood. If you have your questions, remember you don't do chemistry alone. Be free to drop your questions in the comment section and you'll be attended to. By this Saturday, we are going to have a live stream where we are going to do question and answer. So compile your questions. So I will see you there. See you in the next class. Thank you.